Hey everyone! You ready to unlock one of the biggest shortcuts in all of algebra? We're talking about synthetic division. Seriously, if you've ever found yourself just bogged down by polynomial long division, you are going to love this. Think of it as the ultimate math cheat code.
And I'm not exaggerating here. This isn't just, a different way to get to the same answer. Nope. It is a fundamentally faster, cleaner process. It totally streamlines division, and, get this, it has a secret power for evaluating functions that would otherwise be a total nightmare to solve. We're going to get to that.
Okay, just look at the difference. On the left, you've got the old way, right? Polynomial long division, it's a mess. It's sprawling, it's full of variables, and there are just so many places to make one tiny mistake and throw the whole thing off. But on the right, that is our cheat code. Clean, compact, it only uses the numbers that matter. It's just elegance and efficiency all in one.
All right, so how do we actually use this thing? It might look a little mysterious at first glance, I get it, but the actual process, the algorithm, it's surprisingly simple once you see it broken down. So let's just walk through it together, step by step.
Okay, let's dive right in. It really just boils down to 3 easy, memorable steps. First step is the setup. You figure out your box number, and then you just list out the coefficients of your polynomial. Simple. Step 2, a fun one. We call it drop mama. You just bring that very first coefficient straight down. That gets the whole process started. And then step 3, this is where you get into the rhythm. Multiply and add. You just repeat that over and over. That's the whole game. Okay, let's put it to the test with a classic example. We're going to divide this cubic polynomial by this simple little term, x minus 2. Now, if we did this with long division, it'd probably take a few minutes, right? Let's see how fast our cheat code can do it.
So, here's our setup. First, the box number. Since we're dividing by x minus 2, our c is a positive 2. Super important. It's always the opposite sign. Got it? Okay. Then we just grab the coefficients from our polynomial and list them out. 2, -3, 4, and -5. Look at that, nice and clean.
All right, step 2, drop mama. All you do is take that first coefficient, the 2 in this case, and just bring it straight down, right below the line. That's it. This is the number that kicks off the whole chain reaction. Pretty easy so far, right?
And now we get into the core loop, the rhythm. You take the number you just brought down, that 2, and you multiply it by the box number, which is also 2. So 2 times 2 is 4. You take that 4 and you put it in the next column, right under the -3. And here's the key part. You add that column. Don't subtract. You add. So -3 plus 4 gives us 1.
And from here, we just do it again. It's the same pattern. We take our new bottom number, 1, and multiply it by the box number, 2. That gives us 2. We write that in the next column. Now we add. 4 plus 2 is 6. Okay, one last time. Take the 6, multiply by the box number, 2. That gives us 12. And for the final column, -5 plus 12 is 7. And we're done. That last number all by itself, that's our remainder. Okay, so we've got this row of numbers. What does it actually mean? Well, this bottom row is literally the blueprint for our answer. That last number, the 7, that's always your remainder. Easy. Now for the other numbers, the 2, the 1, and the 6. Those are the coefficients of your answer. Just remember, we started with an x-cubed polynomial, and we divided by an x, so our answer is going to start 1 degree lower, at x squared. So that gives us 2x squared plus 1x plus 6, with a remainder of 7.
But hold on, because synthetic division is actually more than just a faster way to divide. It's got this hidden feature, like a secret power-up, and it's all unlocked by something called the remainder theorem. This, my friends, is where this tool goes from just being useful to being incredibly powerful.
So in that last problem, we got a remainder of 7, right? And it's easy to just, write R7 and call it a day. But have you ever really stopped and asked yourself, what does that number mean? What does it represent? Because its real meaning, well, that's the key to this whole thing.
And here it is, the remainder theorem. It's so simple but so cool. It basically says that the remainder you get from dividing a polynomial by x minus c is the exact same value you would get if you just plugged c straight into the original function. So, for our last example, this theorem is telling us that if we calculated p of 2, the answer would be 7. No way.
Just let that sink in for a second. Think about what that really implies. If doing this quick division process with c gives us the value of p of c, then maybe we can forget about the division part completely.
Because it means that synthetic division is secretly the fastest way to plug a number into a complicated polynomial and find the answer. It's not just a division tool, it's a supercharged calculation engine hiding in plain sight.
You don't believe me? Let's prove it. Let's say we have this monster of a polynomial, and we need to find p of 10. I mean, you could do it the long way, right? Calculate 10 to the 4th power, that's 10,000. Then subtract 10 times 1,000, no thanks. Or we can just run a quick synthetic division with 10 in the box.
And boom, a few simple steps later, what's our remainder? 195. That's the answer. P of 10 is 195. No calculating 10,000, no dealing with massive numbers, just a fast, clean, and ridiculously easy way to get the result. Now that is the power of the theorem.
Okay, so now that you've got the basics down, let's talk about mastering this thing. To really make this cheat code your own, you've got to know the common traps people fall into, and you need to see how to use it for some more advanced problems.
Listen up, because these are the two biggest mistakes pretty much everyone makes at some point. First is what I call the sign switcheroo. You have to remember, if the divisor is x plus 3, you put -3 in the box. Second big one, getting it confused with long division. In long division, you subtract. In synthetic division, say it with me, you always add the columns. Get those two things down and you'll avoid like 90% of all the common errors.
All right, let's try a puzzle. This one requires you to think backwards a little bit. We've got a polynomial here, but one of the coefficients is missing. It's k. But we're told that when you divide it by x minus 1, the remainder is 8. So, how on earth do we find k?
Well, we use our secret weapon, the remainder theorem. The problem tells us the remainder is 8 when we divide by x minus 1. What does the theorem tell us? It means that p of 1 is 8. They're the same thing. So all we have to do is plug 1 into our polynomial for x, set that whole thing equal to 8, and just solve the simple equation that's left.
And from there, the algebra is super straightforward. You get 1 plus k plus 4 equals 8. That just simplifies down to k plus 5 equals 8. Subtract 5 from both sides, and there it is. K has to be 3. We just used the remainder theorem to reverse engineer the polynomial. How cool is that?
Now, I know what some of you might be thinking. Okay, that's a neat trick for my pre-calc class, but when will I ever use this? Well, it turns out this little math cheat code has an application that is, quite literally, out of this world.
Now, seriously, the exact same algorithm, in computer science they call it Horner's method, is used constantly to calculate spacecraft trajectories. Think about it. For deep space probes where every single processor cycle and every bit of power is absolutely precious, this method is so incredibly efficient at evaluating polynomials that it's a critical tool for navigating the cosmos.
Kind of makes you wonder, doesn't it? Something we learn in a classroom, synthetic division. It isn't just a shortcut. It's this deep, powerful idea that helps us explore space. So my question to you is, what other math cheat codes are out there, hiding in plain sight, just waiting for us to discover them? Thanks for joining me.